supposed to share with you. I'll do that. I'll do that everything. All right. So hopefully this is visible to all. So the first two part that you're observing over here, this we had actually finished completely. So naturally, first and second module will definitely be there as a part of the syllabus. And as far as the questions are concerned, as I said, mostly we will form our questions on from these two modules itself. But as we have 2 days of time and we are supposed to at least start with a portion of the third module, we are going to consider a small segment of third module itself. Right, I'll just take very small portion of this third module. That also will be there, but don't worry about it. The weightage for this portion will be very, very small. So don't worry about it. And it will be directly, like it will be very easy for all of you to answer. So don't worry at all. All right. So the portion for the third module is up to this part. I'll just make a note of it. Most probably up to this part. That is bipolar junction transistor, device structure, and physical operation. So up to this part, it will be there in the syllabus. Although I might touch upon points till this point, the configuration as well, but most probably that won't be there as a question or as part of the question for your CAT 1. Did I make sense? Is it fine? So module 1, module 2, and the portion till device structure and physical operation. You can say till what I do it today, till today. Okay, not on Friday. Whatever I will finish till today, that is there in the syllabus. Because you might not be aware of what is device structure and physical operation. You might find that it's a huge thing and all. Nothing is that way. But that is the syllabus. So the 2 module as well as a portion of the transistor or the third module up to device structure and physical operation. Anyone having doubt in this?
From each module, you will get one question, no, sir?
Not necessarily, because it's a 30 marks. If that is the case, then I have to include all the 30 for the whole third module also to consider one question. But that won't be the case. As I said, the majority of the question will be from the first 2 modules itself. Like if you can, that maybe I will discuss on Friday's class maybe. But anyway, what the majority of the marks will be distributed from the first 2 modules. And maybe a portion like maybe a 5 marks question or something like that might come from the third module. We actually have to touch the third module by some means. Okay, that's the like a normal rule for all the faculties who are teaching this subject has been made. So that's why, and it's up to the faculty to decide on how much will be the portion. So I am focusing on this small area of device structure and physical operation for the case. Sounds okay?
Yes, sir.
Don't worry, don't worry, don't worry. The silence, even if it is the answer, don't worry about it. It's a very small and insignificant portion that I'm going to discuss, which I don't think will be a problem to any one of you. Okay, so don't worry about it. All right. And as far as the CAT 1 based doubt clearing session or suggestion clearing session, whatever you call it, that I'll do on Friday's class. What we are going to do, we are going to touch upon, or we can kind of a recap on what we had studied so far, as well as we will touch upon maybe some more numericals. I will collect some more numericals by that time, so that I can at least squeeze in as much as problems statements as possible, so that we can understand, we can like get a knowledge of how or what type of questions are we expecting in CAT. All right, so that should be the nature of our mode on Friday. I might also do portion of the third module also, but I am not sure about that. But at least we will do the recap of the whole thing for the time being. That will definitely do. All right, but that's only on Friday. All right. So Divyans, that's fine. Will that be okay, Divyan? Where is he? He only asked the
Sent
question.
in chat.
How do I check the chat? I am out here. Yes, sir. Sorry, sir. My mic is not working. Apology. Wow. He asked the question, then he left. Anyway, because I can't see the chat while I'm sharing my screen, it's not possible to check the chat. All right. So we start off with the third module finally, and the module is called as the transistors. Right. So we have done the thorough understanding of the electronic components. Then we discussed about the junction diode, and that gave us an idea that the semiconductor devices will play a very, very important role in majority of operation dealing with electronic circuits, be it the voltage regulator like a Zener diode, or if it is a PN junction diode which is used as a forward biasing or a reverse biasing condition. And in that way, we are in a way including the amount of current that will be flowing through to the device. So based on that knowledge, when that concepts are extended to a little above level, I would say, that is where the transistors or the transistor family comes in. All right. So in that transistor, we have in the syllabus as the bipolar junction transistor, BJT, device structure and physical operations, that how it works. All right. What is the nature of it, or how the device holds up ideally, as just we had discussed at the PN junction diode also. The same way we are going to discuss about the transistors as well. Similarly, here, just like we had forward bias and reverse bias operation for diode, here we will have something called as common base, common emitter, and common collector configuration, which stands for CB, CE, and CC configuration. All right. And we'll see that each of this configuration has its own merits. Okay. We'll see that one by one, we'll observe that. Then we have the syllabus transistor as a switch or the switching device. Then another set of family of BJT, which is metal oxide field effect transistor, or we will discuss about MOSFET. All right. In fact, this FET, the field effect transistor itself, is a separate topic altogether. So that also I will touch upon. And in fact, in MOSFET also, we have the similar kind of option. You can see device structure, mode of operation, configuration. In that, instead of common base, common emitter, and common collector, it will be called as common source, common drain, and common gate terminal. It will be called as gate terminal. So we'll see that one by one. We'll observe. All right. Right. So what exactly is a transistor? All right. So to understand a transistor, the best example that I thought of, and I think you can also relate to it a little bit more, is that if you consider it to be a tap, okay, just like a tap in back home, in you'll be opening your tap and the water will come out of it, and then you will unscrew it and it will stop the flow of water. That's just the same thing happens with a transistor. All right. So what here you are analogous to is that if you observe that in this particular diagram, suppose we have a current in. Suppose we have a current in. You can see the bottom of the screen, current in. So suppose there is something, how much of the current we are allowing to come out. You can see this current out. All right. So if there is a method in which we can control the amount of current which is coming in and how much of the current is coming out through some mechanism of here, okay, or an adjustable knob or a control knob. This kind of an analogy, or if this kind of an analogy, if you reciprocate to a semiconductor device, that is where the transistor comes in. All right, so that is basically the why it is important. So it is basically, if we read it, a three LED semiconductor device that act as an electronic switch and also an amplifier. In fact, there are many other operations also, but the most important two applications of a transistor is one, it is as a switch. I'll come to that in the next slide also. And the next one is the current amplification. In fact, this is the most important and interesting one. that as we are speaking right now, all right, as we are speaking right now, there must be some way my headphone is amplifying my voice, filtering my voice or audio signal in some way or the other so that it reaches to you without any disturbance. So this amplification part where you are feeding in a very small signal or a very small signal, you can say, and that gets amplified due to some configurational changes is the major advantage of having a transistor. All right. So if you observe in the last point over here that a small voltage or current applied at transistors control lead. So definitely there must be some kind of a control operation there. Okay. That makes a large current flow through its other two leads. This is basically a structure of a transistor. You will find that when you are coming back, we will do experiments on this. This is very easily available. You will have a flat surface over here. This is ideally how it looks. Flat surface over here, and you can see that there is a semicircle kind of element over here. And the three leads which are coming out, one is called as the emitter, base, and collector, or we call it the current in and current out and the control lead, just to compare this analogy. All right. So ideally, by applying some controlling methods or mechanism, we are controlling the flow of current out of the device, which was not there, if you remember, in a diode. If you remember in diode, what we had something like a PN, suppose we had PN. What we were doing, we were either doing a forward bias or we were using a reverse bias kind of or maybe a forward bias kind of scenario like this, or we were applying a reverse bias. Okay, so this is basically where a forward bias is working, because the P is getting in this side and the N is getting accepted over this side. So it's a forward bias kind of condition. But there was no way that we can control the in between whatever the current we are going on flowing, that we cannot control. And there is that is where it lags. Okay. Now the transistor, what it happens is it takes the very nature of a PN junction diode and it kind of replicates multiple times, rather two times, and that generates or that builds the configuration of a transistor. We'll see that one by one. We'll see that. So for the time being, we are assuming that, or we are actually claiming that transistor is a device, semiconductor device, which has three terminal and can be controlled by some means. All right. So let's see how. So then the next point is that these three terminal device are more useful than two terminal ones, such as the diode, because they can be used in multitude of applications. And that is one of the biggest one is the signal amplification. It's a common thing for any signal that you are processing, be it an image, be it a video, be it an audio. So any electronic device, what if it is working with a signal, it will definitely require an amplification factor. And the amplifier circuit will not work without a transistor. Right? Then we have design of logic gates, the binary logic gates that you all know, and the memory circuits also. So all those elements are we require the transistor operation. Now, why do we call it as a transistor? Correct. Why do we call it as a transistor? The basic reason is that we call it from the term transfer of resistor. Right. Now, why it is a transfer of resistor? If you observe in next slide, we will discuss that. In fact, that when we are looking at a current, okay, if you look at just generic way, that current will flow from the resist from a part where you have or rather I would say the current will flow from the higher lower resistance value, because lower resistance means more current, to a higher resistance value, or where there is less current. So it's if you take the if you take the profile of it, definitely where the low resistance will be there, the current will be higher, and whenever there is a high resistance, the current will be lower. So if you consider the analogy of current, if you, anything will flow from higher to lower. Lower to higher is a little difficult. So usually the concentration also will come from higher to lower. So same way, the current also flows based on the resistance. Now, in terms of BJT, in terms of transistor, what happens, if by any means, or rather that is the process, that by some means we can make an effort that portion of the transistor has a low resistance and a portion of the transistor has a higher resistance, then what will happen eventually, because of the difference of the resistance, okay, the current will flow accordingly. And this is why we are looking at the transfer of resistance. Because in case of transistor, you will just now you will find out that the more we go towards the emitter side, there is something called as emitter. The more we are going towards the emitter side, the resistance will be lower, and hence more current will be there. Whereas when you are coming towards the collector side, the resistance will be higher, and hence the current will also be. All right, so that is why it is called as transfer of resistance. That is what we. All right, so that abbreviates to transistor. Now the basic principle is that the use of the voltage between two terminals and to control the current flowing to the third terminal. That's simple what we are observing. In this way, the three-dimensional device can be used to realize a controlled source. That's very important. We can control it, how much we require. And naturally, this three-terminal device can also be used as a switch. We'll see that later. So that's an application. So these are the different types of transistors and the family of transistors, to be honest. If you observe, there are three types, as I already had mentioned in the syllabus itself. One is called as a BJT. The next one is called as a junction field effect transistor, from which the term short term comes in as JFET. You can see over here, I've taken all the first letter JFET. Okay. So this is another type. And the last one is called as MOSFET, which is an abbreviation on top of FET. Okay. So it's an added on thing that happens on FET. And there are different types also, which we will see one after the another as we into much detail for JFET and MOSFET. But for the time being, what we are mostly concerned with is BJT, and that's why there are two basic types. One is called as the NPN, and the other one is PN. If we just observe over here that this is basically a structure of a normal transistor. You leave out this JFET and MOSFET for the time being. All right, just look at this carefully. If you observe that there are three terminals, as we have already discussed, and as I said, the one of the surface is flat surface. So the rule is basically when you are like finding out whether a transistor, how to read a transistor, the easy way is that you have to look at this flat surface. You keep it towards you, okay? So that by keeping it towards your face, the node 1, 2, and 3 will stand as an emitter, base, collector. All right, so that is how it should be read properly. Otherwise, the emitter base collector connections will be difficult, or it will be erroneous, and hence the output won't be come. The symbol for this kind of a BJT is usually of this nature, and we will see that later on also. Suppose the MOSFET will look something like this. It will look something like this. We'll see that how it is, not now, but as of now, we only are bothered with this kind of a terminal of BJT. Let's see what exactly is in store. So this is about the device structure and physical operation that I'm talking about. Pay attention to this very carefully, what I'm about to discuss. So as I've already told you that the transistor is ideally a combination of PN junction, or it's a three-terminal device. Now, if you observe this over here, as a structure suggests, that we actually have, if you observe only this part, okay, if you only observe this red color part, this part is nothing but a NP diode. Okay, unlike the PN diode, this is an NP diode. And you can also observe that between this to this, there is a PN diode. So ideally, it is a back-to-back PN junction diode if they are connected together, if they are merged together to form a single semiconductor device. That will be called as an NPN transistor. NPN transistor. That's the short form of it. If you remember, N stands for the electron majority, P stands for holes majority, and capital N is again indicating the electron concentration. So N, if you observe that here N type is mentioned over here, and this is N type also is there, and there is a very important P type material is also there. So it's a sandwich of the three. But although this diagram is not actually showing it exactly, but you can observe at least that between the emitter, the width of the emitter or even the collector is far greater than what the width we have for the p-type region. So that is mentioned in the second point, that the p-type material, if we are considering an n-type NPN transistor, then the p-type material will always have a very small layer of doping, and it will be just keeping a kind of amalgamation of the two end node of emitter and collector. Okay, so what we are observing over here, that from this it is very clear that if I suppose add a source, if I add kind of a power supply over here, suppose I add a power supply of this nature, then ideally both these two diodes, like if I say PN diode and NP diode, which are the fundamental building block of a transistor, they are as if acting separately as a forward bias device or a reverse bias device. Is it not the case? When we are looking at a structure, when we are looking at this, can we say that there are two diodes which are working together? Okay, not exactly diodes, but there are, we are just imagining it, and they have been given a supply voltage. So based on the supply voltage, the NPN diode or NPN transistor will start to behave in a way where the current and the electrons, or rather the flow of the current, will be indicated based on how or what we are applying at the end of emitter or at the end of collector. So you can observe in the third point, the arrow on the emitter specifies if the transistor is NPN or a PNP junction diode. What is an arrow? You can see if I want to represent this NPN in a symbol, just like we have a register. Suppose I have a register, I'll give this as a symbol. Same way for a transistor, the symbol stands something like this, where your E is emitter, your B is base, and your C is collector. So all of you are clear with this. Emitter is over here, base is over here, and collector is over here. So am I understandable till this point? Everyone? Anyone having any doubt? Now, all right. So now let's see, what does the name suggest? What does the name suggest? Already I told you why this called NPN, because in emitter as well as collector, now we are going to use this term emitter collector. So be very careful in recognizing these terms. So now in emitter and as well as in collector, we have N type semiconductors. So it is assumed, and which is quite a logical assumption, that both at the emitter as well as the collector, we will have majority as what? If it is an N-type semiconductor we are using, what should be the majority in those regions? What will be the majority of carrier in N-type semiconductor?
So electrons.
Electrons. So in this case also, the emitter region, the name itself, it suggests that it will be a very highly doped N-type semiconductor. So what will happen eventually, that it can distribute more number of electrons towards the collector region. All right. So what will happen eventually, that emitter region is emitting electrons. If it is an NPN transistor I'm talking about. If it is an NPN transistor, we are talking about emitter region is a region from where the electrons are emitted. That's why it is called as an emitter region. Correct? Where it will be collected, it should be collected in the collector region. That's why the third term is called as collector region. So collector region is a region of the within the transistor itself where these electrons are going to get captured. That's why the term comes as collector. And in abbreviation, it comes as C. And the base region is nothing but a sandwich portion which connects the emitter and collector regions. It is as if it is just like a platform over which the electrons are moving from an emitter region to a collector. Am I clear? So if this is the structure of the NPN transistor, so definitely the movement of electron, okay, will initiate a kind of current throughout the device. And if you observe here carefully, one very important thing, please observe this carefully. If you have this N-type semiconductor over here, and the majority, as rightly pointed out, is electron. So definitely, whenever we will give some kind of a supply of some nature, okay, whatever be the nature, for example, I might give this as negative. In fact, I'll give this as a negative supply. Instead of this positive, I might give it as a negative supply. I'll just change it. So suppose I give this as a negative supply. I'll discuss this again. No, don't worry. Suppose this is a negative supply I'm supplying. So what will eventually happen? These electrons will get repelled by this negative terminal. And as it will get repelled, it will flow towards this direction. That is, it will flow towards the base region. You can see this is going towards this direction. So as the electron is flowing, I would reduce some unnecessary drawing. I'll just reduce this one, or maybe this indicators. All right. So if the electrons are moving towards the direction as indicated, and as per our rule, as we know that the direction in which electron moves, the current moves in the opposite direction. Please make a note of it. If the electrons are moving towards this direction, okay, because of the supply voltage that we are applying over here, so definitely the current which will be flowing will be towards this, the IE. All right. If I consider the current, so the current will flow towards the emitter side. And if you observe that I've mentioned it in the last point over here, IC, IB, and IE are the respective currents which are generated due to this movement of the electrons. And this IE, if you check the direction, it is coming out of the emitter. It is coming out of the emitter. So it's a physical current which is coming out of the emitter. So you can see in the symbol itself, this arrow indicates the current is coming out of the respective circuit. So ideally, we can say, in fact, very easily that this emitter current is nothing but somewhere a constitution of both IB and IC, where IB is the base current and IC is the collector current. We'll see everything later. Don't get confused. What I mean is, why I'm discussing this, that what is the significance of this arrow? That's what I'm discussing. So if it is an NPN transistor, we are representing it by this kind of a symbol. Like I said, for resistor, we have some kind of a symbol like this. For transistor, we are going to have it like this. But why do I have the arrow over here? To explain that, as I said, in N-type material or N-type semiconductor, we have more number of electrons. And due to the potential that we are applying over here, the electrons will flow towards the collector region. And in the process, as the electron is moving this side, definitely the current will flow in the opposite direction. That's the generic convention for any electrical circuit. The direction of the direction of the current is opposite to that of the electron flow. So as the electron flow is in the right hand side, the current will flow in the left hand side, and the left hand side we can observe that this is nothing but the emitter terminal. So as it is as if coming out of the emitter terminal, so the symbol indicates that this is an NPN transistor, and the arrow indicates that it is going towards the emitter junction. You can see the arrow of the emitter specified if it is a transistor, if it is an NPN or a PNP, with direction indicating the flow of current. Am I clear with this? This is fine. Arrowhead. Why the symbol? What is the significance of the symbol? No answer means
Yes, sir.
you are not with me at this point. Is it fine?
Yes, sir.
All
Yes,
right.
sir.
Yes, sir.
Sir,
Okay.
one question.
Sure.
I didn't fully understand what the role of the p type is, though. If anyways, the purpose is that the
Beta.
emitter region, the electrons from the emitter region go to the collector region.
I'll come to that. I'll just in the second slide only I'll come.
Okay.
Because it might be a little difficult because I'm not discussing about the operation as of now. I'm just telling you what is the significance of this symbol. That's what I am discussing. Nothing
Okay.
else. I'll discuss this and then you will understand. But
Okay, then understood.
fine. Then let's go directly to the way it is going to work. So in that, maybe I'll instead of this, let's discuss about this maybe, or should I go about? I'll discuss this and then I'll go to the convention. All right. Now, along with that, now we are assuming that there are three terminals, NPN or PNP, whatever you call them. And based on that, we are looking at a scenario where there are some kind of there might be a scenario where the electrons or the majority carriers, I'll not say only electrons, because if it is a PNP, suppose this is a PNP, PNP means what should be the majority carrier?
Holes.
PNP. So definitely the majority carrier will be holes. Correct. So it can be electron or can be holes, but ideally, as I said, holes doesn't exist. Electrons will exist. All right. So that's why most of the calculation and discussion in our realistically speaking, they will be in terms of an NPN transistors. Okay. But PNP is also a very common pattern of discussion. So that's why we will keep both these two once after the other, but the operations is absolutely the same. No changes about it. Only one thing, NPN, the majority carrier is, or the dependent carrier that we are looking at is the electrons, whereas for the PNP, it will be the holes. All right. So, and based on that, naturally the connections will also change. Okay. So that's also a factor. Now, if you observe carefully in this PNP, okay, let's finish the NPN, then I'll come to PNP. So in this NPN, what is happening? You can observe the IE is flowing out of the emitter, as I already said. IC is flowing inward towards the circuit. IB is also coming inward to the circuit. So as I said, IE is nothing but IC plus IB. If you apply the Kirchhoff's current rule, it actually works. Same way, if you consider that for the PNP, where it is the opposite way around. That is, when we are looking at this is my collector, this is my emitter, okay, and this is my base. So in this case also, IE, you can see this is combination of IB plus IC. This is clear for us that how the symbols change. And you can observe the change over here. You can see I have mentioned over here. Can you observe the difference? See here. So if the arrow is like this, inward towards the circuit, inward towards the base, that will indicate that that's a PNP transistor that is being used. All right. So the difference between the nomenclature of NPN and PNP has been established by this figure. Naturally, the operations will also be different, just the opposite. One will be opposite to another. So if you know one, you can explain the other as well. Now, along with that, there are certain parameters which you also need to take care of. One of the parameter is called as VCE over here, where CE stands for collector emitter output. What is collector emitter output? So you can see that if you talk about the emitter over here and if you have the collector over here, the difference of potential which you are observing over here, which is mentioned over here, VCE, the difference between the emitter and the collector voltage, that we are looking at as the VCE. Okay, you can say that we are collecting at in terms of output also. You can do that also. You can add a register across the collector and we can find out what is the voltage across it. So that will be a VCE. Okay, each of these parameters has their individual role. We'll see that, we'll establish that later. Similarly, the drop across the base to collector, this is given by VCB or sometimes it is called as PBC, whatever it is. It's a collector to base voltage. All right, and other way around, or you can say here. So it is over here in terms of NPN, it will be like this. All right, and also the other one is VBE, which is the emitter to base. So these are the three voltages. So we have three current, IE, IB, and IC, whereas there are three voltages, VCE, VCB, and VBE. Okay, so all these 6 parameters are crucial for finding out or to maintain the transistor in different operations altogether. Right? So let's see how about a little bit more on the construction side. If you observe here carefully that these are the voltage as I already said, and if you observe the cross section of a transistor, you can observe that the emitter is N, which is placed over here. This is an NPN. The P type, which is forming the base, there is a connector over here. All right. So anything if we want to control, we can add it over here as an emitter, and based on that, the base and the collector will be it. Now you can see the collector is connected to the bottom half of it, which is also an N type, and this is the widest or the width of this region is much more compared to the emitter side. Why? Because it's a collector. The more is the region of the collector, the more it will accept the electrons. And as it will accept more and more electron to pass through, the more will be the current that will be generated on the other side. All right. So that is why the three semiconductor region are divided accordingly. So you can observe the emitter region, that is basically where it is emitting. If it is an NPN transistor, it should be heavily doped. Okay, supply of majority carrier. Simple. P type is the base region where it is lightly doped, because if you make the base also as a very highly doped semiconductor, what will happen? Can anyone tell me that suppose I keep P as very high. If I keep this P or the base region to be very high doped, heavily doped. Okay, so what will happen? Can anyone just Aju tell me then what might happen?
All the holes would neutralize the electrons emitted.
Fantastic. Who's this?
Nitya.
Okay, that's a brilliant answer. Basically, what is happening that if you consider the emitter is emitting the electrons. We have just now observed that these electrons are generated over here. Okay, like not generated, it's already there as a majority carrier, and they are flowing towards this side. And we want the flow to happen, because only until this electron will pass on to this collector and the finally completing the circuit, then only the current will flow. And that is the major concern. We want to make this as a current control device. Okay. So if that is the case, then we definitely require the P type to be very thin as well as lightly doped. It's just that little bit of width that should be provided for the base. Thin, because if it is thin, that means that if you are applying a voltage, there is a high chance that all the electrons from the emitter will cross over to the collector very easily. And lightly doped, because if it is not lightly doped, the holes of the P-type material will combine or recombine with the majority of the electrons from the emitter side. Hence, the supply of electron towards the collector will be heavily affected. So that is why it's always the process of keeping the base to be lightly doped. On the other hand, the collector will also be moderately doped because it is primarily using to collect the majority carriers. If it is already very heavily doped, definitely there will be issues of saturation. But if it is moderately doped, it can also accept the electrons while it is coming in towards it from the nature. All right, so this is about the structure or the physical parameters of junction. So what we have observed, it is a three-terminal device. The basic terminals are emitter, base, and collector. Emitter, base, and collectors are usually comprised of heavily doped emitter, very low and thin doped base, and a moderately doped collector. Also, we have observed the symbols and how they are varying, how the current direction is indicating, or the emitter current direction is indicating the two different symbols. So we'll finish off our discussion for today by this portion, and where we are discussing a PNP transistor. So you can observe that PNP is mentioned over a PNP. So I have specifically took this because most of the discussion you will find it will be based on the NPN, and we will do that also. But at least we can understand from this that the other way around is also correct. So what you are observing over here, that we have a PNP junction, very simple. See that for yourself. This is a P type, this is an N type, this is a P type. So if it is a P type, we have already observed that holes are the majority, whereas for the N type, the electrons are the minority carrier. And again, here the holes are present. What we are observing, that this particular three-terminal device is connected by a voltage supply in a specific order. What is the order? You can observe that the base to emitter voltage. Why it is a base to emitter? It is connected between emitter and the base. That's why it is called VEB. So the base to emitter voltage is connected in a way such that the positive terminal is connected towards the emitter and the negative terminal goes to the base. Okay. On the other hand, between the NP, again you can observe that this part of the collector is connected towards a negative terminal and the positive terminal is connected via base. Simply what will happen, that whenever this plus supply is there as a fixed supply, this when comes something like this, if you follow the arrow and you have the holes present over here because they are the majorities. Okay, they are the majorities. So as it will happen that the P region, they are repelled by the positive terminals of the battery towards the base. Okay, because this is also plus, this is also plus. So plus and plus gets repelled. So this will have a movement towards the way I'm writing the arrow right now. Now, already as I've established already that the base region is very thin and lightly doped. So what will happen? There will be very little recombination that might take place in the base region. Okay, but the rest of the holes will flow towards this direction. So it might appear somewhere over here. And the why it will more come towards this side? Because if you observe the VCB or the VBC, which is the collector to base terminal voltage, this is actually negative. As this is negative, the holes which are here, they are all positive. So this positive will terminals or the positive holes will be fetched upon by this supply, and hence there will always be a movement of holes towards P to N to P, that is from emitter to base to collector, and in that way it will start to flow. But if you observe, if the whole current is like this, definitely my electron, or in this case the if you are looking at the whole current as is the majority of the carrier, so you can observe that based on that we can find out what is the I current which is formed. If I look into this particular segment, the IE current is formed because of this. Because we have made the first part of it as positive terminal segment. As you can observe, that as the depletion region is negligible, the hole penetrates into N region. Although this region is negligible, but still there will be a combination of around very less, like 2% of recombination that might happen from all this number of concentration of electrons or holes for that matter. So very little combinations will happen, combine will happen, and that will be resulted into the base current as well. Base current ideally should be very small. All right, there should not be any leakage current that will take place. We'll see that point later. So this is my IE. That's how the IE is formed. Now, if you look at this base part, as I said, the width of the base is thin and lightly doped. So only approximately 2.5% of the holes recombine with the free electrons on the N region as IB and forms the IB, which is very small. And after that, the remaining holes are drifted due to the application of the negative voltage on the other terminal or the reverse biasing and are collected by the collector. Thus, IC is also formed. So the combination of IC and IB forms the basis of IE. Okay, so this is about the basic operation that we were talking. So let's stop at this junction maybe because it's already time. So let's come back on next day's class and we are going to discuss, as I said, we might finish a small segment on the physical operation itself, as I said already, and we will discuss that and we will discuss that. And as I said, we will discuss and touch upon the suggestions, probable portions and how we have done it over this period of time. Those discussions we are going to do on next day's class. All right, fine, everyone. We'll meet again then on Friday. Please don't miss the class on Friday. All right, thank you everyone.
Thank you. Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks for us.